Hi, this is part 2 of the lecture Linear Dependence and Spans. So let's now consider this set of vectors in C4. Okay, so I'm gonna we can actually call this, these are column vectors, each of them with 4 entries. And this is a set. However, we're gonna use some row reduction in just 1 second. And so, but I want to point out that as a set, okay, so these vectors, we can call them u1, u sub 2, u sub 3, u sub 4, and u sub 5. Okay, and what we are going to address now is the dependence of the set S, and we're going to call the span of S W. Okay, and so it may be that this set is linearly independent, or it may be that the set is linearly dependent, and in such case we can find the smallest subset that is also linearly independent and spanning, and that's the so-called basis. Okay, so to address such a thing, we are in that business of trying to come up with the smaller linearly independent subset of the original set, and this is what I was mentioning. So we now put all these elements u1, u2, u3, u4, u5 together into a matrix. So this is now the matrix formed from the putting the members of the set. So this set S equals that. This is not true. Okay, it is not true that S is a matrix. However, S is, the way we're defining this here, the S is a set. Okay, S is not a matrix. However, we form the matrix with those columns, row reduce, and by finding the RREF, we realize a couple of things. So here R equals 2, and very importantly, the set of indices that we care about contains the number 1, and it also contains the number 3. So we're going to say that vectors u sub 1 and u sub 3, or the first and third vectors, or first and third members of the set S, these are precisely the two members that we would select to form a subset of S, such that that subset is linearly independent, and it also has the property of being spanning. Okay, so a subset with only these two members will have the same span as the span of the entire set. Okay, so, and this remember, we were originally calling the span of S equals W, and now it so happens that because of that theorem that we're learning in this lecture, the subset with these two columns is spanning. So the span of this subset with two columns is exactly equal to the span of the entire set, and also this is a linearly independent subset. So remember, we had mentioned earlier that if we had a set, in this case the set is called S. This set is called S, and we have determined that there are the set is linearly dependent, and we can find a subset. A subset, in this case T, is a subset that contains u sub 1 and u sub 3. Okay, and that subset is linearly independent, even though the entire set is a dependent set. So the other thing we point out now is that if because this set is linearly dependent, we can find an index between 1 through 5 such that one vector with that index can be expressed as a linear combination of the other vectors. So say, for example, in this case, let's talk about the second vector. So we can, because this set is linearly dependent, it's possible to say, we can express u sub 2 as a linear combination that involves all the other vectors in the set. And so the key for making this true is to come up with numbers. I don't know, I'm going to say A, B, gamma, and D, for example. And so this A, B, gamma, and D are scalars. U1, U3, U4 are vectors. So the question is, what are the values of A, B, gamma, and D? What are those values such that this linear combination is indeed true, that we can consider the linear combination be exactly equal to U sub 2? This is the type of question that we would address by forming an augmented matrix, row reducing, and then coming up with a solution set for this particular problem. Here A, B, gamma, and D would be unknowns, but it's possible. We would find that that solution set, this is would be a consistent system, and it would be possible to come up with values for A, B, gamma, and D in light of the fact that this is a linearly dependent set. But okay, so we also come to an end here, concluding, look, there is a wide variety of possibilities for sets T that are linearly independent, which can be employed in a span to create the span of the original set, right? So this W, remember W is the span of the original set. And in fact, we can come up with two other possibilities. Here is a set T prime, and here is another set T star. So recall that those are subsets of the original set S, right? Set S contains 5 members, and we're simply coming up with T star 2, 2, 4, and 2. You can see that T star contains this one, and T prime, and then it also contains 2, 0, minus 1, and 1. 2, 0, minus 1, and 1, so it contains its nearest neighbor to the right. So this is a possibility of a linearly independent set that also is spanning. And then T star is another possibility. So can you prove, and this is left to you as an exercise, can you prove that these subsets are linearly independent? I'm going to give you a hint. You would use row reduction. You would use RREF to address that. But can you also prove that the span of each of these is exactly equal to the span of the original set S? So that I leave you with that as would be the equivalent of a reading question.